All right, so I'm Bernhard with Fluence Labs. I got Alex here with me, and we're talking about stream processing at scale with decentralized data pipelines. I would be remiss not to also bombard you with a data deluge slide. High volume, high velocity, high veracity, and basically, I mean, David already addressed it, but there's so much data coming in that we don't even know what to do with it. If we do something with it, we don't even know necessarily where it goes and if it's properly utilized. And that's fundamentally the definition of big data, right? Previous to big data, the volume and velocity and the difference in variety and veracity was very, very different, and data could be managed with cool things like SPSS and SAS. That changed, big data evolved, and we're really sort of driving these 4 V's in the big data paradigm. And most people look at, I don't know, maybe you don't, but a lot of people look at big data predominantly as batch processing, driving the training of ML models, basically using data at rest, usually high gravity, to do prediction analysis and all that good stuff. However, a very critical aspect of big data is actually stream processing. It used to be called real-time analytics. And in stream processing, you operate on data in flight. That eventually leads to the augmentation of existing batch blobs wherever they are, Filecoin, IPFS, doesn't matter. And the major V's of stream processing are around usually volume and velocity. You kind of know what structure you get. Structured, unstructured, hybrid structure, you're pretty cognizant of that, what's coming in streams, because you control them to a certain degree. And some of the improvements in stream processing are around in-memory processing. RAM's gotten really, really cheap, so that really, really changes everything. Because in many respects, for stream processing, you often want to operate in the millisecond window, mini batch, if you will, up to seconds. So RAM really makes a difference on how to do this. And then, of course, cloud and increasingly serverless are drivers of modern stream processing. So if you look at Confluence around Kafka, for example, they are now advocating very, very strongly using a function as a service to do intermittent stateless processing. So those are sort of certain attributes right now in modern stream processing. In order to process streams, you got to move data. In order to move data, you need pipelines. And also there have been a lot of improvements, and some of the key attributes of modern data pipelines are around distributed architectures, particularly fault tolerance and failovers, and the way you handle checkpoints. And exactly once processing is one of the most important checkpoints right now. On top of it, you have sort of a governance and monitoring about what data security, sort of the data engineering aspect that is very closely tied to data pipelines, which also separates the data engineers from the data scientists for very interesting debates most of the time. But moving on. So big data is big business. There's lots of data. Big data paradigm is huge, and there is pretty much a solutions for everything. A lot of them actually are open source. Apache has taken really sort of a very dominant foothold in the open source provisioning of tools and processes, as well as file formats. So it seems like a very, very well-served market. The centralized cloud providers have very strong support on pretty much every aspect, leading all the way up to providing optimized OSS implementations for GPUs to train your models at various cost points. So why talk about decentralized stream processing in pipelines? I mean, it looks like everything's working. Looks like there is a huge ecosystem. A lot of it is open source. And even if you have content addressable storage like Filecoin, why not just build on centralized cloud provider offerings to utilize the cheaper, better content addressable storage? And if you do it, how do you do it? So before I answer those questions, about 4 years ago, I'm probably I always mangle her name, but Zhamak Dehghani, she came up with the concept of data mesh. It's not quite in the in the same league as data warehouses, data lakes, lake houses, but it's a socio-technological construct. It's a process construct that has identified a lot of attributes where data management, particularly big data management, processes, tooling, and the use of the outputs fails massively within organizations. And if you look at the attributes she identified and the transformation she's been proposing, a lot of these attributes and transformations align very, very closely with Web3. We look at decentralized ownership. So domain ownership in her case is only the people who are skilled enough and knowledgeable enough about the data should be involved in handling the data. But it comes back to a little bit further down. From architecture, distributed, technically, you want data and code as one unit. That's a really, really important one, because from a verifiability perspective and auditability perspective. And on it goes. Anyway, so there's a lot of, I don't know, controversy, but a lot of discussions about the merit of data meshes. But data as a service and data as a product with ownership within enterprises or organizations is certainly for real. And this is one of the answers or attempted answers to it. What matters more for this talk and for our discussions is that a lot of the pain points in organizations handling data are aligned very, very well with the solutions Web3 has to propose, and decentralized solutions have proposed. So what are decentralization benefits then? Cost reductions by many X for data and compute. We're coming from the compute side, and we'll get to that in a little bit, are significant. Auditability. Consensus, if optional, distributed architectures, ownership control, reduced barriers to adoption of data and code as units, and governance. And one of my pet peeves or favorite topics is managing business continuity risk. If you interact with third parties, if you have counterparties, you usually accept a long tail risk, such as deplatforming and other catastrophic failures. Low probability, high damage. Very, very difficult to price, and often not easily priced because you have many different stakeholders in an organization. However, if you are, and this in the age of cancellation, it's very easy to violate a business terms of service. Anti-platforming has been taking place at a much faster rate than it has in the past due to changes in our culture. And that's very, very expensive. If you have petabytes of data and you have till the end of business day to move it, then there's a pretty high chance that your business is done. And that's an enormous risk. Other risks associated with continuity is vendor lock-in and, of course, exit barriers. Again, it's just something very difficult to price, and in my opinion, as well as Gartner's, Forrester's, and others, it's massively underpriced. So a lot of the cloud pricing is actually deceptive in the sense that it's not fully priced. So it's actually a lot more expensive on the tail than you actually would expect. And that's actually very, very significant because it's one of those intangibles that are just not fully actualized in a lot of decision making. So how do we go from, so back to stream processing, this is where we come from. So we had the little journey here. Amazon, for example, has a stream process that includes serverless. And they use Kinesis Stream plus some other stuff to deal with the actual streams, the acquisition, and as an intake sync. And then they use Lambdas, which is their function as a service, to do some processing and putting it into DynamoDB. Well, on the decentralized approach, we can actually counter that offering to a very high degree today. So for example, Ceramic Streams, David just talked about Ceramic, they're a great partner, built on IPFS, is one way to look at replacing MQTT Kinesis or even Kafka to a certain extent. On the key value storage, again from Ceramic, ComposeDB, for example, is an increasingly strong contender and beta now, so it's starting to look really, really good. And of course, on the serverless, this is where Fluence comes in, so that's us. And now I want to talk a little bit about Fluence. Fluence is a decentralized serverless stateless peer-to-peer compute protocol. So basically, you want a decentralized Lambda. the function as a service. And it's an open permissionless peer-to-peer protocol. It's a decentralized capacity marketplace, which is on-chain. And it's basically function as a service off-chain. And it's built around WebAssembly, which gives you a high portability. We also have almost done proof of execution and validity, which is an on-chain proof right now, and have a bunch of tooling and a DAO coming. So basically, in a nutshell, what you do is you take your business logic, you express it in WebAssembly. Currently, it's in Rust, Python, and JavaScript are coming. And that business logic is then compiled to WebAssembly. Those WebAssembly modules, we call them now a service, can be deployed to one or more peers in the peer-to-peer network, which is open and permissionless. And we have a general purpose WebAssembly runtime called Marine. That's part of every reference peer in the network. In order to interact with those services, which are not HTTP accessible, they're only peer-to-peer accessible for a variety of reasons, including our strong embrace of the Web3 ethos, so we really don't want to deal with the censorship risks that come with DNS. You need something. You need a workflow engine, and we wrote our own. It's called Aqua. It's built on derived from PyCalculus. And that lets you choreograph and compose these distributed services into workflows. So basically, if depending on your intent and capability, you can build a distributed, even decentralized applications and protocols, if that's what you want to do. And everything is off-chain, except for the marketplace and the validation. And so here's sort of a little bit of an overview how the marketplace and some of the validation works. So Aqua, when you execute it, it basically leaves or gives you an execution trace. That execution trace can be sampled and can be validated with the very same virtual machine that validates that manages the execution of Aqua on each peer as a WebAssembly module currently on Near. So there's a smart contract, which is literally the virtual machine, and you can run probabilistically sampled execution traces and validate whether or not the execution has taken place and taken place correctly, which then leads to payment and/or slashing. Right now, this is on Near and the Aurora testnet, and we are ourselves in testnet, and we are moving to mainnet in Q4. And as part of that mainnet, we're moving everything to Filecoin, to FVM and FEVM, including the Aqua virtual machine. And that's basically where we're with that. So going back to what we want to do is we want to do this serverless component with Fluence, and the way we can do it today is we can compile some of the Apache error tools to WebAssembly. I have it in a little less transparent because we didn't quite get it done. DuckDB is also something we have almost ready for WebAssembly. And then we write custom WebAssembly modules to interact with other pieces, including Ceramic Stream and ComposeDB. Okay, so how do we go and do it now? So want to do some examples. So let's say you have some devices, could be peer logs, could be temperature sensors, doesn't really matter. Dumping data into ceramic streams instead of Kafka, for example. And then you use Aqua and Marine services, these WebAssembly modules, to build crawlers. So this is actually very close to the Amazon Glue analogy. Amazon Glue being an integral part in their serverless stream processing offering. And one thing you can do with Aqua is you can use one-shot clients, you can have long-running clients to execute it, because the execution of Aqua happens actually on the peers that host the services that are being called. And you can actually deploy Aqua as a scheduled script, if you will, as a cron job on one or more peers. So you have this polling capability to deploy crawlers that now look for data changes, updates in the database, in streams, etc. And then push this into other logic, like stream processors, for example. And stream processors can actually end up in two pipelines. For example, an event trigger. So for example, you have data windows you compare to threshold values that then trigger events. And of course, driving that data into your persistent sinks, such as Filecoin, for example. And there's something very, very cool, and I don't know if we have enough time to go through it, but Sergey from Camo addressed this in a very, very good talk last year. So if anybody is interested in data meshes, and particular Apache Parquet file format, you really should listen to the lecture from last year, is driving Parquet files. And we'll get into that in a little bit. But what we basically can do is we can build highly decentralized data lakes on top of IPFS or Filecoin in an entirely decentralized, with a highly decentralized serverless component today. It's absolutely possible by choosing existing interoperable file formats and tooling. So at this point, we want to go a little bit into examples, a little bit of code, and the next few slides are for you.
Thank you. Hello. So as Bernhard said, we have this thing called spells that are basically a recurring orchestration action. So it's a workflow that takes a bunch of things, glues them together and says, you do that, you do that, you do that. And it's distributed so it can tell what to do to different nodes, to different peers across the network in different data centers, all that. So we have a language for expressing all this distributed workflows. It's called Aqua, and it has a nice property of being when you design something in Aqua, it's very clear from a system design perspective what's happening, what components are involved, because it's very simple and it works with interfaces mostly. So here we're talking about crawlers, so we need to read from ceramic stream or whatever source you have. Right now it's ceramic stream. So here are the components that we will use to do that. So we have service called ceramic stream that just basically gives us CID of the mutable stream, the tip of the stream, the actual value of the latest one, after applying all the commits that ceramic does internally. We have a service that is able to work with files locally on local peer. We have a Parquet service that also locally able to compress one file and provide a new path that returns your Parquet compressed file. And we have estuary to upload to Filecoin, assuming all the keys are inside and managed by the compute providers. So we have that, and here is how the crawler looks like. It's pretty simple. What would you expect? The word spell basically means here that this is a recurring execution. So what we do here is we read from ceramic on line 27, then we take from local key value storage, we take the last tip that we saw on previous run. So you can imagine this function runs every 3 seconds, every 5 minutes, whatever you configure. And so we have to see if there were changes, and if tip of the stream changed, then now we can download the actual content and put it to a file. And once a file reaches certain size on line 32, we can go and compress it through Parquet and say, estuary, please upload it to Filecoin and provide us CID back. And what we do here, you need, you upload files to Filecoin for some reason, so you need to be able to read them back. So you need to be able to maintain the CIDs where you put the files on Filecoin to retrieve them back. That's exactly what we do on line 35. We just put it to local key storage and say, here are list of all the Parquet files that we uploaded, and whatever your business logic is after that, you can just take the CIDs. For example, a function Filecoin files just takes the CIDs, and you can do whatever you want with them. Maybe you want to orchestrate some other data pipeline with some other spell. But that's a very simple example of gluing a bunch of different technologies together through a simple script. And here it happens on a single peer, But since it's a recurring task, it actually can involve more peers into it. And you can imagine this just scaling to something we call subnet. So you pay a bunch of money to blockchain and say, I want this happening on a bunch of peers, reading from a bunch of streams, and all put into Filecoin, and then I will do something with those files. So that's basically what's happening here. That's how you can build simple crawlers with Fluence, and that's how you orchestrate different services. I guess that's it. So yeah, as I said, it's possible to scale this orchestration process to something called subnet, and once you have that, you have a certain problem of service discovery, right? When you have a single peer and you know its address, its public key, you can find it in the network. But when you have a dynamic subnetwork of different peers running these orchestration flows, you have a bunch of them. Some of them are dying, some of them are returning back, someone just usual failover happens. You have to have some service discovery for that. And we have this pattern when we have a thing called registry. That's basically a distributed hash table where you can where different workers register themselves by the deal ID. Deal ID is the kind of name of the contract on the blockchain where there are money paid for. That's basically paid job. So we have this ID of paid job, and everyone who does that job, they register themselves like, I'm doing this job. And you're able to reach them through this resolve subnetwork that internally uses Kademlia and all that things that you probably know about. And it gives you back a bunch of workers, and you can go to all of them and say, hey, give me what Filecoin files you have uploaded so far. You can ask for different logs, states, how many errors happened, how many executions happened, what are the metrics, like how long it took to process. All that is there. But here is a very simple example of just getting all the results from all the crawlers that you paid for. And you can hear on the line 50 that it happens in parallels. It involves distributed algorithm, like a distributed orchestration workflow, and on line 54, we're just waiting for everyone to reply us. We can have more complicated logic here with like that things about who is up, who is down, but this is a very simple thing. So we in parallel wait for everyone to answer us, and on line 55 we say, okay, if a certain amount of time passed and we didn't have all the answers, return what we had. So for example, if we have 10 workers, only 5 answered, then after 10 seconds we'll just get 5 results. That's basically it. That's how you can do complex orchestration in seemingly simple fashion.
All right.
Thank you.
Let me just get through a few slides, and then we can take questions. So we've done a bunch of data processing. We have streams. We capture the streams. We did something with them, and now it's time to write to file. And one way to do this is to write to Parquet, and Apache Arrow is a complete solution to do this. We managed to compile. I managed to compile Apache Arrow, Polars, which is basically a Panda type library in Rust, and Parquet Crate as well. So if anybody's interested in how to get this into WebAssembly, it's not entirely straightforward, but it's not super difficult. So I probably can accelerate your journey there if that's something you want to do. And as I said, we have DuckDB coming. And if you look on the right, this is your Marine. This is your Rust code right now to handle the file writer. Now, as I mentioned before, in Fluence, you have peers. Peers have some capabilities to execute WebAssembly files, WebAssembly modules, and track the state of the execution of your workflow. Everything is stateless. So how do you deal with state? So what we do in handling the state, we integrate it with IPFS. So we have an entire library ready for you to use that basically allows you to use IPFS through Aqua. So you're bridging two different peer-to-peer networks with one orchestration tool. And in the right, basically what we're doing, and you get the file name and you build this path. And then you start just basically, this is just normal Apache arrow file writing into a Parquet file with all the metadata and all this good stuff. On the left, you have your Aqua that actually orchestrates that marine service to do that. And what we do here is we set things up, we get our topology discovery in place. We do this through line 26, and then we start writing our data, which is part of the data schema, which itself could actually be a JSON document coming from either Ceramic directly or IPFS. And then we write it, and then instead of writing the file directly to the file system, we write it to the file system, and then we serialize it onto IPFS. And this is what's happening in line 29. And that's actually a highly efficient way. Now, the other part to consider is WebAssembly is single-threaded. You may want to write multiple streams to multiple files, or funnel multiple streams into a single write. And in Aqua, you have parallelization capabilities. So you can run, you can basically fork your workflow, run it across a whole bunch of different peers. So if you wanted to have 10 different file writers, you could do so, and then you can bring it back at the end. And that's actually extremely powerful. And if you look at it, I mean, the right side, this is all there's to it. I mean, this is just how Apache Arrow writes files. This is what you need to do. And on the left, this is the entire orchestration of that from a possibly distributed stream source or data source back to a distributed, like IPFS, could be Filecoin, or Estuary, as Alexei pointed out. It's very, very quick, very, very powerful, and actually quite efficient. So I have a little bit of time, not much. So one of my interests in this whole thing is basically decentralized data lakes and lake houses. And instead of how it's done right now, you have these Parquet files, which are industry standard. They're in your object store, which is usually S3, and then your metadata is in DynamoDB. It irritates the bleep out of me, and I really want to see a lot of this moved into a decentralized environment. And Parquet is a key to that. It's not the solution, but it's a key to it. And in part because it's not, aside from the fact that it's columnar, blah, blah, it's actually an immutable file. And the key immutable is that it's accepted in the industry as a standard to be immutable. Now, just because it's immutable doesn't mean it's content addressable. And it doesn't have any hashes yet, and order matters. So if you have your data in different order, you get different immutable Parquet files. However, Sergey from Camu, he's really onto this, and he's already has a crate which actually compiles to WebAssembly, we have it working, that allows you to start hashing parts of Parquet file content. And it's, again, still not fully content addressable, but it's striving there. And this is something where the community really could and should pitch in, if anybody's interested, because this is, in my opinion, a very, very critical key to get towards decentralized data lakes and the open source, community-driven approach to big data. David pointed out that I think it was the second or third slide. So, in summary, decentralized stream processing and data pipelines are possible today. They are probably not as high capacity as you want them to be. We're a few years behind the big players, but it's certainly possible and tangible. We can already emulate significant solution offerings from cloud providers. And I think Web3 native solutions end-to-end are certainly possible and highly valuable, and capture a lot of value that can be redistributed. Plenty of room for improvement, however, and so looking into the room here for taking charge. Next steps, we need to build out these decentralized ecosystems, and from our perspective, anybody who's interested in decentralized serverless for big data, please reach out. As I said, we're going to mainnet at the end of the year, so there's a lot possible for us to become involved with you and help you to achieve your goals. If you're interested in content addressable Parquet and decentralized data lakes, love to talk to you one way or the other. And if you're interested in DuckDB for in-memory processing, it's actually really cool. If you haven't looked at it, if you don't know it, you should look at it. It's part of what's increasingly termed the modern stack. And please reach out. And how do you do it? Well, there's a bunch of links you can follow up and contact us. Thank you very much for your time. If you have any questions, fire. Yes?
Thanks. I wanted to ask a question about Aqua, the language. It is suspiciously similar to Apache Beam, kind of inspired thing, isn't it?
Well,
and the question then would be, was a deliberate choice to kind of have a language and not adopt a similar SDK implemented in like what people are used to, like, I mean, Google Cloud Data Flow and things like that. And then you would basically get all the users that code and that stuff.
Yeah, so the key to Aqua, so Aqua is, yes, I mean, it obviously took inspiration from existing solutions. As a foundation, though, it's rigorously built on PyCalculus. So every operation is fully representable and traceable in PyCalculus. That's already a big deviation. And it's really, really important because if you want off-chain verification and auditability, you have to have that. One. Second, Aqua doesn't just manage the workflow. It injects a massive, massive abstraction layer between bare metal libp2p. So peer discovery, content routing, all this stuff is highly, highly abstracted from you, for you. And that's an incredible component of the implementation of Aqua. Because Aqua, I should have been more explicit. Aqua is a language. Aqua is a compiler that takes this language and compiles it into an immediate representation. And Aqua is a virtual machine that interprets the intermediate representation at the peer level. So it's really an ecosystem. And so yes, at the high level, there are possible, I mean, there are workflow engines that are close. And from a semantic perspective, we are looking at re-implementing the front end because, as I said, it's a compiler, so we're actually looking at a JavaScript or a JSON document type-based approach into specifying your parameters for the workflow. And we are looking at other workflow engines to maybe get a certain overlap in DX. Let's put it this way.
Thank you. That answers the question perfectly. And I have another question, if I may, very quickly. What's the runtime story, like latency, reliability,
okay.
QoS?
Well,
and
all right. We're in testnet, so it's kind of tricky. It's kind of tricky.
What's the approach?
Actually, Alex A can speak to it a lot better, and I don't know if you have any Grafana charts you can pull up real quick, but
no, I can show later some. We have some Grafana graphs. So the WebAssembly runtime it runs like on Wasm time, and it's rather close to bare metal in that sense. It's like 2x or 3x slower or something. And since Aqua is just telling libp2p send this that and this to other peer, it's just like the network latency is what you get there. There's more or less no overhead in principle to that. So there is a certain overhead going to WebAssembly in and out, but that's optimizable. So in principle, there's not much overhead involved. It's just telling things what to do when.
The interesting overhead will be like the ultimate cost of decentralization compared to the centralized platform.
Yeah, so, well, there's this fundamental problem when you scale your discovery networks like Kademlia to a certain degree, and I guess IPFS folks can speak about that at length. There's a certain problem that the high churn, and in effect, the Kademlia becomes slower, and it could take days to resolve something. So our approach, since Aqua gives you really powerful tools for system design, and our approach right now, what we're trying to do internally is to have hierarchical Kademlia, when you have one big Kademlia that does not actually address all the discoveries, but instead it manages a lot of small Kademlias that are kind of targeted to single task. So when you have a lot of peer doing similar jobs, it's in a small Kademlia. And this way you can have one layer of hierarchy, or you can have n layers, and this way you kind of solve this scaling problem of Kademlia. At least we hope so.
Hello. Sorry. I've got two questions. One, which is too long to talk about, which is I'm desperate to know how you compile perlers into WebAssembly, because I've failed, but I'll talk to you about it afterwards. And the second one, more interesting, is could you say very quickly anything about how you do the probabilistic verification of the WebAssembly? Because that's something that we're interested in doing, and so we'd love some tips.
Okay. The white paper is in progress, but basically, so if you're familiar with the lottery system used by LifePeer, for example, or the golden ticket, whatever they're called, Samori, or whatever the blockchain is. Anyway, it's a lottery system, and you identify. I have to step back. Pure WebAssembly modules are deterministic, and based on that, you can make certain assumptions. You get the trace. And all you need from the trace is so it's a very long answer. Part of it, so let me just give you the intro right here, and then we can take it offline. The way Aqua works is we have something called a particle. A particle is a smart packet. A smart packet consists of data, the compiled Aqua script, which is called air, and some metadata. You package this at the very beginning, so you have your genesis data. So if you have a service hello parameter, your parameter hello COD summit is the only piece of data that goes with that packet. You have a client. The client could be short-lived, long-lived, doesn't matter. Flings this, literally the smart packet, onto a relay. The relay starts looking at that packet, what needs to be done, do I have the service? No, now this whole Kademlia work starts kicking in, route discovery, content driving, blah, 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 into the next peer, where hopefully we have the service. On that service, Aqua Virtual Machine starts looking at the script, what's been executed, what hasn't been executed, and starts instructing basically the WebAssembly to run those WebAssembly modules. All along those steps, you get signatures from the participating peers, ingress and egress, hopefully. It's going to be a BLS where you basically you get constant size, blah, 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 and it's very verifiable at the content. So what you basically have, you have this the signed custodial chain, if you will, that can be expressed in hashing. And if there's a break in the hashes, you know that something hasn't been executed properly. So when you start sampling probabilistically, as long as the hash changes, it's not entirely dissimilar to how the Merkle trees work in blockchains. You can do probabilistic sampling and then rerun these pieces, and if the pieces are successfully rerun, in terms of signature matching, blah, 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 all this stuff, then you get a hit. As I said, it's probabilistic, but we think we can get it to a really, really high probability. So that's roughly how it works. If anybody any more questions, we'll be around. Thank you.